everybody, it's Mrs. Pound, and I am here with the very last video in our chapter on reflection and refraction. So our objectives today are going to be to explain how a prism separates white light into colors, describe the conditions for a rainbow, and describe the process of total internal reflection. So first, let's talk about dispersion in a prism. Dispersion is the separation of light into colors according to their frequency. You can see that refraction is occurring. Red is refracted less. The frequency of red is refracted less than violet, and everything else falls in between. And so that is why they are bent differently. They actually travel at different speeds through the glass of the prism, and so they are refracted differently. The spectrum produced by a prism or a raindrop is evidence that the average speed of light in a material depends on the color or frequency of light. So each frequency will travel at a different speed in the glass. Now let's talk about the rainbow. The rainbow you see is not the same as the rainbow somebody else standing next to you sees. You must stand in the exact same spot to see the same rainbow. And in fact, you are standing in the center of your rainbow that you see. If you move, you will still be in the center. So you can never find the end of a rainbow. The outermost color of a single rainbow is red, and we see that here it is the red. We're going to watch some videos in class about the formation of a rainbow, but the reason that a rainbow is red is actually in order to see a rainbow you have to have the sun at your back low in the sky, and you have to have raindrops in front of you. The image that you are seeing is not formed by raindrops behind you, it is formed by raindrops in front of you. And what happens is the light goes into the raindrop, it refracts, it reflects off the back of the raindrop, and it comes out back at you. So it is formed by the raindrops in front of you. Now, when it does that, the purple is actually on top. But the weird thing about this is that you can only see a single color from each raindrop that you're looking at. And so the raindrop that is blue that is coming at you is actually lower than the raindrop for the red, and so it is reversed. And when we watch the video, that will explain it, and explains it much better than I do, and so that's why we're going to watch some videos in class. Now, if you see a double rainbow, what you will notice is that blue is the outermost color. Look at this. It's like it's a mirror image, right? Red on top here, red on the bottom here. Blue outside, blue outside. So it's like a rainbow sandwich with red in the middle. And this is due to double refraction. And again, we are going to watch a video that explains this better than I can. To show that you're listening to today's video, what I want you to do is I want you to draw a rainbow next to this section heading on your paper. So draw a rainbow next to the section heading for the rainbow. Now, the last topic we're going to talk about is total internal reflection. With total internal reflection, there's something called the critical angle. This is the angle at which light doesn't refract but reflects. And for water, this is 48 degrees from the normal, and for glass, it is 43 degrees from the normal. And we see this applied in things like prisms, diamonds, and fiber optics. That's why diamonds are so brilliant because light gets trapped in there and reflects um, against all of those facets in there. That's why they sparkle inside. So total internal reflection is the 100% reflection with no transmission of light that strikes the boundary between two media at an angle greater than the critical angle. So if we go back to those critical angles that we wrote down, they have to be that angle or greater in order to have total internal reflection. And an application of that is optical fibers. I'm sure you have seen these before. Um, I have a picture there. This is a transparent fiber, usually glass or plastic, that can transmit light down its length by means of total internal reflection. These are also used for communications because they are super fast. The speed of light is 186,000 miles per second. And in a glass fiber, the light will travel at speeds of 124,188 miles per second. So that is the speed of light in glass. So it's not as fast as the speed of light in a vacuum, but it's still really fast. Light travels in a curved optical fiber, so it can be curved. Sometimes doctors use these so that they can bend the light to do surgery and things by internally reflecting in a succession of straight line paths. So we see here these reflections are greater than that critical angle going down and reflecting off of the walls of that fiber. And so that is how the light gets to the tips here at the end of an optical fiber. So our objectives were to explain how a prism separates white light into colors, describe the conditions for a rainbow, and describe the process of total internal reflections. So write your 5 questions, and this is it for this chapter.